Welcome back, everybody. We are now going to proceed to the next feature. It's not a clause. So technically, the list of clauses that we covered is pretty much complete, I think, right? Select, from, where, group by, having, order by, limit, offset, in exactly that order. So this is something you should learn by heart, so that you remember that. Okay. Joining. Joining is not a clause. It's not a clause. It's something that we will see is going to be done in the from clause between tables. So as usual, I want to show you the reminder of what we've been doing before. So in the theory, we saw that we can join two tables. In that case, you see they have the column B in common, right? Which is an integer. So column B and column B in both R and S. That means that we are combining the records of both sides, but not in any way. We are combining them when B matches. So you see here, 1 matches with 1, 2 matches with 2, and this one doesn't have any match, right? So it means that we have two combinations, the combination of this with this, which is right here, and the combination of this with this, which is right there. We also saw that the symbol that we use is this sign right there, that is like a multiplication sign, but we add these two vertical bars on both sides. So it's like the Cartesian product, but with the extra vertical bars. This is called a natural join, right? Gets these results. Right now, so Mark, who is moderating today, told me he's experimenting with making domains collide for joining. Do we have results yet? Not yet. Okay, it's like on a TV show, right? You have somebody working on something, and we just check from time to time. So we'll come back to you to see if you figured out what happens if we have different domains here and here with PostgreSQL. All right. Also, just so you know, we have other fancy versions of this symbol right there, where we only have one vertical bar on one side. There is another version with 2 extra horizontal bars and so on and so on. Maybe we look a little bit into that, but it's because there's plenty of more kinds of joins. There's the semi-joins, there's the outer joins, there's the semi-outer joins, then the left outer joins, and so there's plenty of versions of that. But for now, I'm sticking to so this is the natural join, it's the simple version. And the theta join, which is the same, except that you have these additional predicates. So this is like, if you want, you know, in many devices, let's take your internet box at home, right? You're connected to the internet, you have an internet box, then you go to the UI for the settings. By default, you will have a user-friendly UI. And then there is a scary button in somewhere that says expert mode. Wow, expert mode. And then you click on it and suddenly plenty of extra things pop up, right? So you could consider that this is the easy version that you get. And if you click on the expert mode button, then this is your expert mode, right? You switch to expert mode, and then you get to actually specify your expert thing in there, right? So A equals D, which is your what you want to test, right? And in particular, if here, sorry, if it doesn't match in this natural way, you need expert mode, right? Theta join. Okay, but this is something we saw last week, right? Okay, now, yes, it doesn't work. Okay, so maybe you can explain the microphone, your findings.
Okay, I just tried out on a Jupyter notebook if the domains have to collide on a natural join, and they have to collide. PostgreSQL is giving me an error. It's saying operator does not exist, character varying equals small int. So it cannot cast a character to a small int.
So it's basically throwing an error. Okay, so this answers your questions, right? That you asked on the element chat. All right, awesome. So now we have our answer. Okay, so basically you need to make sure also in PostgreSQL that this domain here is the same as the domain there. All right. Okay, now let's join these two tables. Now I have two. We used to have only one table, now we have two. So we have a table with people. These are the Star Trek characters. And then we have a table of spaceships. So we have Enterprise A and D, the original Enterprise, and USS Voyager. So here we have the captain name. So as everybody knows, the original one plus the following version was Kirk, then Picard in the Enterprise D, and Catherine Janeway in USS Voyager, right? Then we have the codes that are standing on the spaceships, and here we have the warp speed, which is a number between 1 and 10. That is basically the speed compared to the speed of light, and the maximum warp is 10. There is even an episode with warp 10 that is quite funny. So it's like the SQL databases, right? If you do warp 10, weird things happen. It's like if you try to put limit and offset without an order by. Okay, so we want to join. What is the thing we want to join on? Could we do a natural join? Well, it doesn't seem like it, right? We don't have any columns in common, right? Name doesn't appear here, captain name also not, code also not, and warp also not. So first, the natural join will not work, right? We cannot count on a natural join. But we have expert mode. We have expert mode with the theta join, so we get to specify our predicate. So what are we going to match here? Well, we would very much like to match the captain name right here with the last name of the person right there. In fact, if you look, you have some things that correspond, right? You have Kirk right here, you have Picard right here, and Janeway right here. Right. So we are going to join with a theta join, the expert mode of joins, last name of persons matches the captain name of spaceships. Now, the predicates syntax is the same syntax as we used for selections in the where clause, right? We already saw that. You can use equals, not equal, greater than, lower than, and or not, addition, multiplication, even the trigonometric functions and square root and cubic root and so on. So it's exactly the same syntax as in the where clause. In fact, it is so much the same syntax as in the where clause that we are going to use a where clause. So we are comparing the last name of the person with the captain name of the spaceship, but the new thing that we didn't see in there is in the from clause. You might notice that we have two tables in there. This is new. We have persons, comma, spaceships. This is something we hadn't seen before. In previous queries, we just had one table, and then it was a predicate on just one table. What's new in here is we have two tables in the from clause, persons and spaceships, and we say with this little dot in there, we have the table name on the left of the dot and the attribute name on the right. We say the person's last name must be equal to the spaceship's captain name. This is what is returned because we also project on just century and warp. So this here and this there. So we have the century and the warp. I will take the time to explain the query, but before I explain, who already understands what's going on here? Some of you. Who doesn't yet? I will explain, right? So it's okay if you don't. Who doesn't? Maybe you don't dare say. Okay, let me explain what's going on. In terms of query plans, let me explain the query plan here. What happens is we take the table persons, we take the table spaceships, and we do the Cartesian product, right? How many records do we get in that Cartesian product? 16, yes, I hear 16, 4 by 4, right? It's 4 on the left, 4 on the right, so you have 16 possible combinations. Of course, it's a Cartesian product, so the Cartesian product you don't even think, you just combine everything with everything, right? So you even have a combination of this with this, and so on, right? So all possible 16 combinations. This is a Cartesian product. That's the first thing that happens in the query plan. Then we have the where clause. What does this where clause do in terms of relational algebra? It does a on Zoom, maybe. What does the where clause do? A selection, yes, exactly, it does a selection. So it selects, in the 16 tuples, it's going to select the ones where the person's last name matches the spaceship's captain name. And here you see what are not all the 16, but the combinations that match is this and this, this and this, this and this, and this and this. So there are 4 out of 16, 4 records are actually surviving, right? Okay, we're almost there. But these 4 records, they still have all the columns. How many columns do we have in these records? How many attributes? There is no trap. 9, exactly 9, all of the attributes. Why? Because when you combine with the Cartesian product, you keep all the attributes, right? And there are no collisions of attributes, so that also makes it easy, right? So we have 9 attributes. So now we have 4 records and 9 attributes. The next thing that we do in the relational algebra, that's the select clause. What do we do? Projects, yes, we project, and we project to the 2 attributes we have, century and warp. We don't need to specify the table because it's unambiguous, right? So we just say century, it will take it from here, and warp take it from there. So now we go from these 4 records with 9 attributes, squeeze to just the 2 attributes for these 4 records. And in fact, this is our output. It's a bit hidden, but I have this magic trick that you showed to me to remove the Zoom UI. So this is the output with 4 records. These are the 4 that survived this predicate, and the 2 attributes, which are the 2 that we projected right there. So now, who understands what's going on? Okay. What's very important is that what I have been explaining in the past 2 minutes is the how, not the what. I showed you one way that you could compute that. There can be others. There can be other ways. Another way to compute it, let me give you another how, another query plan that would compute exactly the same thing. Let me look at these 2 tables. First, I'm going to only keep last name and century in the table persons. So I'm starting, right? It's very adventurous, right? I'm starting with a projection. I'm projecting this table to just last name and century. Then I'm projecting this table to just captain name and warp. So now I have 2 tables with 2 attributes. Next, I do the Cartesian product. I get 16 records with 4 attributes, which are last name, century, captain name, and warp. Then I execute my filtering predicates, which gives me 4 records with 4 attributes. And then out of these 4 attributes, I only keep 2 of them, century and warp. Who agrees it's exactly the same result? It is, right? That's called an optimization. What did I do? It's called a push down. I actually eliminated useless attributes from the very beginning. I basically noticed that first name, middle name, captain were useless for this query, and that name and code were useless for this query as well. So I just don't even read them from disk. That saves a lot of time. So what we've just done here, actually took at the example of this query, is that we generated 2 different query plans. And in practice, what the database management system is probably going to do is probably going to pick the second query plan, because that's going to be faster. What's very important to understand is in SQL, we specify what we want, and it's PostgreSQL's job to figure out how to actually execute it. Okay, that's a lot of things, right, for just one query, but let's now come back to the join. So we wanted to do a theta join on persons and spaceships. So I put them in the from clause, comma separated, persons, comma spaceships. And in the where clause, I specify my theta join predicates, the subscripts under the theta join. Okay. Now, this is one way that works. You can absolutely do it in that way. Nobody will complain. This is a pretty standard way of doing a join. But it turns out that SQL has a syntax, an alternate syntax that allows you to do exactly the same thing. This is the same thing. You just, instead of the where clause, you put the theta predicate in the from clause. So you basically say persons join, now it's explicitly a join, persons join spaceships on person's last name equals spaceships captain name. This is called the table expression. So it basically means that now we are looking at the from clause specifically, and we are seeing that the from clause can actually be more complex than just one table name as it was before. This is called the table expression. And we can also do a lot of things in there to prepare the table in the from clause. This is the same thing, right? It's exactly the same output. It's just a different syntax to do exactly the same thing. Which one to prefer? I don't know. Both of them are good. It's a matter of personal preference. Right? Some people like it this way because it's simpler. Some people prefer it this way because they enjoy the fancy advanced features of PostgreSQL and the SQL language. Okay, but now that we've opened the box of the from clause with this join keyword in there, we can explore more. Do we have a question?
Maybe, yeah. There's a question on the Zoom chat. So there is no advantage of speed with join, or in comparison to cross join.
Exactly, there is no advantage of speed. How do I know that? It's because if you look at these two queries, there is the same information. In both queries, you're saying you want to join persons and spaceships, and you specify a predicate. There is nothing that there is here that is not there, and there is nothing that is here that is not there. It's exactly the same thing. There is absolutely no difference in performance between the two. It's just that if you use this syntax, you're basically just opening the door to plenty more new features of the language. This is basically the entry point for more features. Did I answer your question? No difference at all. Okay. Why no difference? Because we have an optimizer. Because otherwise you could have argued, no, this is a join. This here is a Cartesian product followed by a selection. That would be inefficient. But as I said, since we have an optimizer that will automatically recognize the join, the speed will be exactly the same. Okay. What would be slow, just to come back on that, is if you don't have any where clause. If all you do is select from and then you put two tables without any where clause, then you're really asking for the Cartesian product. This is going to be slow if the tables are big. But as soon as there is a where clause, I'm not getting into the algorithms, but there has been plenty of research on how to efficiently compute joins, and joins can be very, very, very fast. We have plenty of magic tricks in the computer science toolbox to execute joins very, very fast, even with millions of records in the table, right? I'm just not going to scare you with the algorithms. We can use hash tables and all the like to do these things. Okay, but no difference between the two. Okay, now here's the more syntax there. If you want a Cartesian product, you can also use cross join. Cross, just like the cross of the Cartesian product. This here is the same as just a comma, right? If I showed you earlier with the comma, this is the same as persons cross join spaceships. It's just that the comma is a shorthand for that. Okay, so cross join is just the Cartesian product. Here, I didn't want to throw 16 records, so that's the reason why I actually shortened the tables a little bit to prevent the table explosion, but basically we have 2 and here and 3 here, so the Cartesian product has 6 records. So you see it's all combinations. So you see 3 times with Kirk, 3 times with Crusher, and here we also duplicate here and here. That is my Cartesian product. Okay, and again, this here is the same thing. I don't mind if you put cross join or comma, it's all the same. Okay, you know it's the same thing in any language, by the way. In Java, in Python, you very often have several ways of doing the same thing. Yes, there is a question over there, maybe the microphone. Yeah. For the people on Zoom, so that they can hear us as well.
You had mentioned about a push down optimization thing for the previous slide. Yeah, like to get the same output, like we project the 2 columns that we need first and then do the selection. Could you please tell us the SQL query for the same?
Oh, you don't need a SQL query. You can use a SQL query, so you could. I will also tell you what the SQL query will look like. What is important to understand is that when you do optimizations, you don't actually work with SQL. You work with the query plan. The query plan is like an abstract view of SQL, right? So what's going to happen is that the query plan will be created, and then the software is going to reorganize the query plan and then execute. However, you can also take a query plan and create the SQL for the query plan, right? So you could absolutely write an equivalent SQL query for the push down. The way this query would look like is, and don't be scared, everybody else, because this is advanced and this is something that will come, I don't know if we'll have time today or next week, but this is with a nested query. You can actually, as we will see later, nest a select from where inside another select from where, right? Like a recursive thing. And what you need to do to implement that push down is, instead of persons here, you open parentheses and nest another select from where. In that select from where, you will project to these two columns. Then you say as persons or whatever name you want to give, then comma, then again, instead of spaceships, you have a pair of parentheses. You put again the select from where, select, in that case, let me do it explicitly. So select century warp from, open parentheses, select last name, comma, century from persons, close parentheses, and then as persons, comma, open parentheses for spaceships, select captain name, comma, warp from spaceships, close parentheses, as spaceships. And then you can keep the rest of the query as it is. The good news is, as a user, you don't need to do it, because the system will do it for you automatically. This is why people don't actually do that, why they do not actually do the projection. They 100% know PostgreSQL is taking care of it, right? That's the benefit of having a relational database management system as opposed to writing things in Python or Java. You get this for free.
The query you mentioned would just make, if it's a big table with say hundreds or thousands of records and columns, then it would give you the output much faster in the second type of query, the nested one.
So let me give two answers. If you do write the query with this push down, replacing persons and spaceship with a projection to the columns, it will not be faster. But the reason it will not be faster is that if you don't push down, the optimizer does it anyway. That's the reason why it's not faster. Right? Does it make sense? But internally, it will do it. Okay? All right, any other questions? Okay, but these are really good questions. The notion of push down and optimization is actually important to understand for in the context of database systems. So it's, I'm really glad you asked that question. Okay. All right, cross join, comma. Okay, here's another one. I told you there's many kinds of joins. This is when you start having these special symbols that I didn't bother you with, but it's all the variations of the join symbol. A join by default is an inner join. So this is the same thing as join actually. If you say join, you can also say inner join, it's equivalent. Why do I tell you that? Because it turns out there's also outer joins that I will explain. But what we've seen so far is in fact called an inner join. What does it mean? It means that when there is a match, it will do the combination, but you might have records on the left that do not match with any record on the right. And you might have records on the right that do not match with any records on the left. In that case, can anybody give me an example of records that is basically alone, that doesn't get any match, left or right? On Zoom, maybe. Yes, I hear you want, so the microphone. I see also on Zoom, we'll see if you had the same idea.
The pressure one?
Yes, exactly. So the second record on the left, Beverly Crusher, she's the doctor, the medical doctor. She's not the captain. So this is why she's not on the right. So the second tuple in persons does not match anything on the right. What does it mean concretely? In our case for the join, she doesn't appear in the output, right? If you look at the output, there is no records that would have Beverly Crusher. This is what an inner join is. In an inner join, if you have records that don't match anything, then they are not in the output. For whom is that clear? Okay. And again, I repeat, inner join is the same thing as join. If you say join, you're implicitly saying inner join, right? Very important. Okay. Okay. So this is indeed, and congratulations also to you on Zoom who gave the same answer. I saw it pop up on the screen. That's indeed this tuple here that doesn't get any match. So now you might, as a user, would like to do the join. Yes?
So is there any difference between inner join and join?
No difference. It's the same. Inner join is just a more verbose way of saying join, but it's totally equivalent, right? It's exactly, you know, we have examples of that. For example, when you define your table, if you do not say null or not null, by default, it's as if you said null, right? So there's a lot of implicit things. Here it's exactly the same thing. If you say join, you are implicitly meaning inner join. You can say inner join to be more verbose, but it's equivalent, right? Okay, another question. I saw a raised hand. Maybe I imagined the raised hand. I thought somebody was raising their hand. Don't hesitate to raise your hand again, right? If you want to ask a question. Okay. Inner join. Okay. So now we come back to this example where one of the tuples does not match with any tuple on the right according to our theta join predicate, the expert mode. What if we still wanted to include Beverly Crusher in the output? But of course, it wouldn't be with any combination from the other table. But what if we want to do that? We can. We can with the magic words. It's like in Harry Potter, we have these magic formulas, and here the magic formula is left outer join, and left outer join is going to include the tuples from the left. That's why we say left outer join. So Beverly Crusher now, C Crusher false 24. But then on the right, there is no match. That's not a problem. We know how to do it in PostgreSQL. We just put nulls everywhere, right? So since there is no matching spaceship, we just put null, 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 null all over the place, and that's it. I suspect here, I'm not 100% sure. I suspect that if there are default values, it might be that the default values would be used instead. Not entirely sure. This is also something we could experiment on. But if we don't have any default values, for sure, it's going to be the nulls. Okay, for whom is that here? The left outer join, right? So this is the difference. Inner join, you wouldn't include the tuples that don't have matches. And the left outer join would also include the tuple from the left who do not have matches on the right. The tuples from the right that don't have any match, in that case, there's none, but if there had been some, they would not be included in the outputs. Then we have the right outer join. So here I modified the data a bit. So now I removed Jean-Luc Picard from the list of the persons. So now we have a spaceship, Enterprise D, that doesn't have any match on the left. We can still include the spaceship in the output with the magical formula, right outer join. Now we're saying the tuples of the right, the records of the right that don't have any match on the left are still in the output. And then we just paint with nulls the entire left side of the output with the attribute of the left. Okay, so this is the right outer join. It's just the symmetric equivalence, right? Right and left. Then you might want to do both left and right, and you can. And then the magical Harry Potter formula is full outer join, in which case you include both tuples. Maybe I can, for the people in the room again, make sure to show everything. There you go. So you see now we have the three matching cases. So Kirk, Kirk, again Kirk, Kirk, and then Janeway, Janeway. So the three that match, which are here, here, and here, plus those that don't. So we have this tuple right there, here, that doesn't match anything, so we put nulls. And then we have the tuple from the right, right here, that doesn't match anything, so we put nulls. This is a full outer join. Who is following? Right, this is relatively simple, right? Very visual. Okay. Okay, so now we know inner joins, left outer joins, right outer joins, full outer joins. I didn't show you the symbol. There is actually a symbol in the case of the relational algebra. If I'm correct, it's the same symbol as the join, but you add some additional horizontal bars on the left, on the right, or on both sides to get these. Maybe I can show them to you next time, how they look like. They exist. I don't know if there's a Unicode. Maybe there's a Unicode for them. They exist in LaTeX. I'm almost sure they exist in LaTeX if you want to use the symbols. Yes?
I just tried to look if the null values are get replaced by default values. It's not the case.
It's not the case.
Not
Okay,
the
great.
case.
So basically, even with default values, it's nulls everywhere. Great. Thank you very much for this, Mark. Okay. Okay, but everything we've done here were theta joins, right? Why? Because we had a predicate, right? On every slide, there was this equality predicate there. What I haven't shown to you yet is the natural joins. How do we do natural joins? Well, here's how. You just use the keyword natural, right? So in that case, it's a natural full outer join because yes, you can combine. You can do a natural inner join, a natural left outer join, a natural right outer join, or a natural full outer join. So here we do a natural full outer join with the two tables. Why? Because now I modified the name of the attributes, and you can see now they are both called last name, and this is what I get, right? So what's the difference with the theta join is that now there is one attribute less, right? You can see there's only 8 attributes. This is because since it's the same, and since anyway we make them match, there is no reason to duplicate them. So this is why we merge these two like this. For whom is that clear? Okay. Yeah, so I wanted to show you also there is the inner join, which would, what did I do here? Oh, yeah. I'm saying be careful. Why be careful here? Yes, I know why. Now remember. What I did on that slide is I introduced a collision on purpose. I renamed another attribute. I renamed basically century and codes. They both start with C, so I just changed to C. And now we have a problem because in a natural join, you're joining on all the attributes that are the same. It is the case with C and C. And on top of that, they are both integers. And as Mark established, if the domains didn't match, that would be different, but they have even the same domain. But now do you see what's happening? Last name and last name here, we are fine. This is what we want. But here, C means the century, and here, C means the code. So now, if you were maybe very optimistic, okay, let's go ahead with a natural join, bam, Pech gehabt. It's totally empty. It's totally empty because of the C and C that basically never ever match. So this is why when you use natural join, be careful. If you use a natural join, make sure to look at the schemas of your tables and make sure that the columns in common are really intentionally matching, because otherwise this can happen. If you have a doubt, then just put your predicate in there and specify the predicate explicitly. Okay. There's so many bells and whistles in PostgreSQL. The syntax gives you additional shortcuts if you're lazy and you have a situation like that with a collision of attributes, but you're too lazy to write an entire predicate equality, right? You don't want to actually have to go through adding on persons.last name equals spaceships.last name. In that case, for the lazy, there is the using construct. You can say persons full outer joins spaceships. If you don't specify any predicate, it's going to be a natural join using last name. And here you say it's really just the last name colon, right? And you specify here the attributes you want to match. This is a theta join, but it's just that instead of writing explicitly the entire predicate, you're just saying the attributes that you want to use.
There's one more question on Zoom. What happens if C has different domains?
I I think it would be an error, right? This is what you showed earlier. So Mark experimented earlier and found out that in PostgreSQL, if you try to join on attributes with the same name and different domains, you get an error, right? Does it address your question on Zoom? Awesome. Okay. Okay. So there are two things here that I'm saying. The first is that using, it would be equivalent to explicitly writing on persons.lastname equals spaceships.lastname. If you're too lazy to write on persons.lastname equals spaceships.lastname, just write using lastname. It will do the same thing. For whom is that clear? Okay, so you see how computer scientists, how we reason. We are so lazy. Whenever we have an opportunity of making our life easier by finding a shortcut that makes us write less, then we just go ahead and do it, right? Okay. All right, and if you have a collision in that case, you don't want it to be a natural join, that would be name and name, but you have the name of a person and the name of a spaceship. You don't want to join on that. Just use using, and then you say, okay, it's the last name with the last name.
There's one more question. How can the spaceship code be an integer when it includes letters? Did I miss something?
No, you didn't miss anything. I missed something. So that's just my mistake. So I need, oh, there's many slides. I will need to replace integer every, oh, wow, that's going to be a lot of work. It's everywhere. Yeah, this was correct. So all I will need to do is just replace this integer with varchar on all these slides. So it's my homework to do. Thank you very much for catching this. Okay. And the second thing here I wanted to say is, if you don't say anything and don't specify an on criterion, then it's natural. It's assuming natural. Yeah. What is your question? Yes, exactly. Here it's because it's so either using or on. Again, I can't guarantee that you cannot use both using and on, but I would be scared of the consequences. So probably an error we can test, but I wouldn't suggest to actually mix them. Okay. So you see using is for use whenever your natural join would work in an unintended fashion, like here you don't want to join on these attributes here. Okay. Also, you probably want to rename, because here you have another problem, is that you have two attributes with the same name because you didn't join on them. So technically, PostgreSQL would probably write persons.name and spaceships.name in there to disambiguate. What I recommend you do is use the as to rename here. So you say P like persons, P name and S name, and there you go with different attributes name. So be careful, again, if you see that you have the same attribute, but you don't join naturally on these attributes, then rename them to avoid issues like here. Okay. I'm thinking, do I still have time? Yes, one last thing. You can also rename tables, right? Renaming columns is with as. You can also rename tables like this. To rename a table, I think you can also use as if you want, persons as P and spaceships as S, but it also allows you to not use as, to just say persons P and spaceships S. It sounds a bit like in an object-oriented language, right? Where you just have the type followed by the name. So it's just because it's intuitive, right? And then if you give an alias and call this table P and this table S, then instead of persons.name and spaceships.name, you can use the alias right there. Okay. Okay, I think I'm going to leave you alone for today. We learned a lot of things. I'm just going to check that you followed. I need to scroll down again. Where are we? Right here. Okay, so here I'm just checking that I was actually making sense today. Okay, that's good. So the majority is above 80%. Okay, so of course you'll have exercises, right? So the best way to learn is to actually just sit in front of your Jupyter notebook and just type as many queries as you can, experiment, play, solve the exercises. You will have that at the exam too, probably, that you will query, will give you a data set and you write SQL queries. So it's highly, highly recommended that you spend as much time as you can making yourself familiar with the SQL language. Plus, it will be super useful in the future when you have projects like semester's theses, master's theses, and so on, querying data that is tabular. Okay. So thank you very much, everybody, for coming. You even have 5 minutes back. You can go to the Mensa and not have to queue. Enjoy the exercise sessions. Thank you, Mark, for moderating today, and I'll see you next week, as always, at 10 next Friday. Thank you very much.